Welcome to this eLearn Security video training lesson on iOS application decryption. In this video we're going to see how to decrypt iOS applications. You should know that almost all of the applications available in the iStore are encrypted, meaning that if we tried to load them into software such as IDA or Hopper, these tools would not be able to correctly disassemble them. We do have different methods to decrypt encrypted binaries, and we are going to see a few of them in this video. The first method is completely manual, and we will have to calculate and dump the decrypted application from the device, while in the second method we will use an external tool that will do all of the work for us. Our target application in the first part of this video will be the application WhatsApp. The first thing to do is download and install the application on an actual device. In our case, the application has already been installed, so we will simply navigate the applications folder in the device, and then we will download the binary onto our local Mac. We do this because we want to verify that the tools such as IDA or Hopper fail to disassemble the application since it is encrypted. We will reopen the decrypted app at the end of the entire process to demonstrate that this decryption works. So let's start a connection with iTunnel in order to use FTP through the cable connection. Now that the tunnel is set, let's open CyberDuck and establish the connection with the device. Now navigate into the WhatsApp folder and download the binary onto our Mac. So here is the binary. Let's copy it over to our machine. Now that we have the binary, let's open IDA and load WhatsApp. IDA identifies two architectures. Let's select one of them and click OK to continue. As we can see, IDA warns us that the file is encrypted and that disassembling this file will be useless. Let's continue anyways and see what happens. Let's click Yes in the Objective-C alert and continue. Once the tool completes its operations, the binary is loaded. But as we can see, we are not able to read anything in it. In the function window, we see a lot of odd method names, while in the main window, the commands are completely wrong. This is because the app is encrypted, and IDA, of course, is not able to disassemble it. So now that we are sure that the application is encrypted, let's see how we can manually decrypt it. The first step is to verify if ASLR is enabled, and if it is, we have to disable it. We do this because we're going to dump the decrypted application from the device memory, so we want to be sure to dump the correct area. You should know that in the latest versions of Xcode, the flag for ASLR is automatically set. So almost every application has the full ASLR enabled. To verify this, we can use OTool. Let's open the new terminal and move into the folder where the WhatsApp binary is stored. Now let's run the command OTool -VH against the binary and check the values in the column flags. As we can see, both architectures have the pi flag, meaning that the application has been compiled with full ASLR. Once again, in order to decrypt the application, we need to disable this option. Otherwise, we will still be able to decrypt the application, but it would require much more effort. This is because in order to get a decrypted version of the app, we are going to run the app on the device, and then we are going to dump the portion of the memory where the app resides. Of course, when the app runs on the device, it will automatically decrypt and be loaded into memory. Otherwise, it would never work. So if ASLR is not enabled, we can easily calculate the area to dump. So now that we know that the app has the pi flag, let's see how to disable it. To do this, we are going to use a Python script written by the Chromium authors that is available at this address. We have already stored it on our desktop, so let's see how to use this script. It is very easy to use. We just need to run the script with the option --no-pi, followed by the binary and press return. So in our case, the command will be python change mock opy.py no pi WhatsApp, and then press return. After a few seconds, it ends without any error or warning. So what had happened? Let's try to run otool again and see if anything has changed. Indeed, as we can see, the pi flag is gone. So it seems that everything went correct. Let's try to upload the binary back onto the device and verify that the application still works. We can copy the binary back to the device using FTP, but first, let's create a backup of the app. Now that the app has been uploaded, let's connect to the device via VNC and verify that WhatsApp still works. Let's open a new terminal and run iTunnel again. This time use the port 5900, which is the VNC default port number. Now that iTunnel is working, let's open VNC Viewer and connect through the tunnel. So here's our device, and there's the application WhatsApp. Let's start the application and verify it still works even after the changes to the flags. As we can see, the application seems to work fine. Once again, let's try to close the app and reopen it. It works fine. Now that we have disabled the pi flag and we have verified that the app still works, let's move to the next step. In this phase, we need to gather some information from the application binary that will help us to calculate the correct area to dump once the application is running on the device. We already know that the application is encrypted, but we can also verify it by running the following command. Here we can see that the crypt ID value is 1, meaning that when the application starts on the device, the operating system will try to decrypt it. This command is also useful because it gives us some valuable information necessary to calculate the area that we need to dump. For example, cryptoff is the offset of the encrypted data, in other words, where the encrypted data starts. Crypt size tells us the size of the encrypted segment. We need one more piece of information to proceed, and we can get it by running the command otool -l WhatsApp. Let's go to the very beginning of the app and let's locate vmadder for the __ text segment. The correct value is the one that has the CMD value set to LC_ segment and the seg name set to __ text. So the value we are interested in is vmadder. If we want to directly display this value, we can also filter the results of the previous command concatenating some grep commands. For example, we can use the following command and get only the output that we want. Once the command completes, we see we have the same value as we found before. So let's summarize and write down all of the values gathered. Cryptoff is 8192. Crypt size is 3145728. Let's verify these two values by running the OTool command again. Here they are. The next value is the starting address, which is the 0x, 4 zeros, a 1, and 3 zeros. Now we need to perform some simple calculations. First, let's sum the crypt off value with vmatter to calculate the starting address of the decrypted area. Let's open the calculator and sum 8192, which is converted in hex as OX2000 with the vmatter 0x1000. So the starting address is 0x3000. Let's now calculate the address range to dump. This can be calculated by adding the value of crypt size to the value just obtained. So we have to sum this value to the crypt size, which is 3145728. So the range to dump is OX303000. Let's write this value down. So what are these two addresses? Once the app runs on the device, it will be loaded somewhere in the memory of the device. This range is the exact area that we have to dump to get the decrypted app. Now that we know it, we can move forward to the next step. In this phase, we have to run the application on the device and actually dump the area using the tool called GDB. So let's open VNC and check if the application is running. If it's not, just run it. Now let's connect to the device through SSH. With the app running on the device, let's create a new tunnel for the SSH via the cable. We are going to use iTunnel once again to forward our port 8888 to the SSH port on the device. Now let's establish the SSH connection to our local port. As we can see, we have an SSH shell on the device. In order to dump the decrypted area from the phone, we need to use GDB. Since we need to attach GDB to the process, let's find the process ID with the following command. So here's the PID of the WhatsApp process. Let's attach GDB to this process with the following command. We'll use GDP -P followed by the app's PID. Let's wait until GDB finishes its operation and we should get a new prompt. Here we are. GDB is attached, and as we can see, our prompt has changed. From this shell, we have to run the memory dump command in order to dump the area from the memory. To do this, let's run the following command. Dump memory, followed by the name of the file that will contain the dumped area. For example, let's set it to whatsapp_decrypted.bin. Then insert the two addresses that we had calculated before. The starting address is 0x3000 while the second value is 0x303000. We can now hit return and wait until GDB dumps the area. Now that the area has been dumped, let's quit GDB with the Q command. Now let's run ls-l to verify that the file has been created, and we see here that it has. We can verify that we have dumped the right range by checking if the size of the decrypted bin is the same as the crypt size. We see they are the same, so the range should be good. The next step now is to merge the original binary with the decrypted portion just dumped. So we are going to replace the encrypted portion of the app with the decrypted area dumped before. So let's go back into our FTP client and download the dumped area onto our box. To merge the two files, we can use the dd command. In the terminal, let's write the following command, dd space bs equal 1, where bs sets both input and output block size to 1 byte. Then we'll add seek equal 0x3000. Seek skips in blocks from the beginning of the output file before copying. Then we'll add conv equal no trunc. Conv equal no trunc does not truncate the output file. Then we'll add if equal whatsapp underscore decrypted.bin. If is the input file. Next is of equal WhatsApp. Of is the output file. If everything has been set properly, this command should overwrite the decrypted application into the original app. Let's run the command and wait for the results. So it seems that the command worked, but we need one more step to complete our decryption process. We have to change the binary crypt ID value from 0 to 1. This is necessary because if it is set to 1, the OS tries to decrypt the app once it's run. But since it's not encrypted anymore, we need to set it to 0. This instructs the OS to load the app without trying to decrypt it. Let's check once more the crypt ID value before changing it. Here we can see that the crypt ID value is still 1. To change these values, let's open the binary into a hex editor. Now let's search the following hex value. Here we see it. The crypt ID value is located 8 bytes after. So that would be right here. So let's set the editor in overwrite mode and change 01 to 00. Note that since this is a fat binary, we need to set the crypt ID twice. If we search the previous hex value again, we find another match. Here again, 8 bytes after, is the crypt ID value set to 1. So let's change it to 0 and save the binary. Now that we have completed our decryption process, let's verify once again the crypt ID values. As we can see, the values are now set to 0. We can copy the binary back to the device, but first let's close the application from VNC. Let's go back in the FTP client and navigate until we find the folder where the app binary is stored. Now we can overwrite the encrypted version with the new one by copying the new file onto the device. Let's click Continue to overwrite the file. Now we can check if the application works. As we can see, the application is working fine. It seems that everything went right, and now we should be able to load into IDA without any problem. So let's reopen IDA and load the new binary. As we can see, the warning about the encrypted application is gone and we can continue. Let's wait until it finishes to disassemble the app. IDA is now able to completely decompile the application, and we were able to see all the methods, names, as well as the bytecodes. Of course, now we can also inspect all the strings hard-coded in the binary. IDA doesn't have any problem with loading and displaying them, so the decryption process worked just fine. As we have seen, this decryption process is not very fast and requires many steps and many operations, but there are some tools that allow us to do the same steps in much fewer commands. One such tool is called Clutch. We can find it in the App Addict repository, and it's called Clutch Patched. As we are going to see, once the tool is installed, we just need to run one command to obtain a decrypted version of the target application. This time for our test, we are going to use the application Dropbox. So let's go back into our FTP client and let's download the Dropbox binary. Once again, let's try to open it in IDA and see if the application is encrypted. As we can see, IDA displays a warning that tells us the file is encrypted. So let's continue and see what happens. As we saw previously, we are not able to see the plain text of the binary. Everything in the binary is encrypted. So let's close IDA and see how to use Clutch. To use this tool, let's go back into our SSH session and move into the Dropbox folder. Now let's run the command clutch Dropbox and wait until the tool ends its operations. As we can see, the tool automatically gets the encryption information that we had gathered before with OTool. Once it finishes, we can see that a new .ipa file has been created. Let's go back into FTP, navigate into this folder, and then download the IPA file into our Mac. As we already know, we can inspect IPA files by changing their extension to .zip. Now that the extension has been changed, let's open the archive and navigate its folders until we find the Dropbox binary. Here it is. Let's copy the file onto our desktop and then load it in IDA. As we can see, the warning message about encrypted content is gone, and we can click OK to continue and let IDA decompile the app. Since the app is quite big, it will require some time for IDA to finish. Once IDA finishes its tasks, the app has been successfully decompiled. This means that the decryption with Clutch worked. Here we can see all the methods names, as well as the opcodes of the application. Let's double check that all information has been decrypted by opening the strings view. As we can see, everything is now in clear text. So as we have seen, thanks to Clutch, with only one command, we are able to obtain the decrypted version of the app. What we have seen in this video is how we can manually decrypt applications by removing the PI flag to disable ASLR, then dumping the decrypted application directly from the device memory, and then merge the encrypted version with the decrypted dump. However, this manual process is very time-consuming. In contrast, we have also seen how to use Clutch, which does all of those steps for us and returns an IPA file of the decrypted application. Thank you for joining us.